All right. On Zoom, can you see the normal slides, or can you see with like the notes and the next slide and all that stuff?
I'm seeing the presentation view, like the notes.
All right. Let's swap this. How about that? Should be good to go. Yeah. All right. Thank you. Thank you, thank you, thank you. All right, so today we are talking about visual attention, yet once again. On Wednesday will be your review for your next exam. I know it feels like you just had an exam, and you did just have an exam, but when I've done fewer exams in the past, students haven't liked the pressure associated with that, and so we're doing more frequent exams. So we'll do the review on Wednesday, and then your exam will be a week from today. And yes, it will only cover these 4 lectures. All right, so your fun fact of the day is that on Good Friday in 1930, the BBC reported there's no news, and instead they just played piano music. Can you imagine how much nicer the world would feel if all of these 24-hour news cycles just said, actually, there's nothing really we think you should care about, and here's some piano. I think everybody would be a little happier. Ooh, I forgot to put in the what did we talk about last time slide. So what did we talk about last time?
Visual attention.
Visual attention. Okay, Sydney's gonna fail for her sarcasm. What else do we talk about? Or what do we talk about within visual attention? Allie says selective attention, focusing on one object. Exactly. Yeah, so the classic example we showed is the, what's his name? Dan Simon's gorilla experiment, right? Where you had selectively attended to people passing the basketball per the requirements of the video. And then a gorilla walked in, right? And if you had seen that before, you knew to be looking for the gorilla. And so you were selectively attending to the gorilla, and you probably missed what was going on in the background. So the change in the color of that backdrop, as well as one player just leaving altogether, right? Exactly. Anna says the Posner cueing paradigm. Yes, so the Posner cueing paradigm, again, indicates that I can cue somebody's attention even if they're not changing where they're actually looking in that field, right? So if I presented up here on the screen a fixation cross, told you to keep looking at that cross, I presented some red square there on the left, and then took that red square away and then presented a stimulus, there would be a benefit in terms of reaction time for responding that that stimulus occurred on the left. Even if you hadn't moved your eyes, you've shifted your covert or overt attention.
Covert.
Yes, covert, exactly. Yes, good job, Anna. You have shifted your covert attention to that. Perfect. And so last time we talked about the Sieve model. Can somebody give me what the Sieve model predicts and what are the components of the Sieve model? right, so we have 4 different components for the Sieve model. S stands for, oh, I thought your hand was going up here.
No, it's counting in my head.
Oh, okay. S stands for salience. E, there are 2 E's, but it's typically represented. First E stands for effort. The second E, or the third letter, stands for expectancy, and the V stands for value. And that Sieve model predicts what?
How much you retain or notice what you see.
Sort of, kind of. It predicts the probability that you're going to attend to a piece of information. So not necessarily the retention, but what's the probability that you're going to attend or pay attention to that information? Right? So as salience increases, so too does your probability of attending. As effort increases, your probability of attending goes down. Right? So if you're requiring somebody to move their whole body, it's less likely that they're actually going to see it. As expectancy goes up, so too does the probability of attending. Right? So if you're expecting an important phone call, chances are you're not going to miss that phone call. And then the value, if that isn't in fact important phone call, chances are you're going to be more likely to pay attention to it. Questions about that or anything we covered last time? All right. Let's go ahead and get started with today's lecture then. So one big component of visual attention, or one of the ways we study visual attention, is with visual search tasks. So visual search is just what you do on a regular basis. You're looking for your car keys. You're searching the environment until you find your car keys. And in that case, we call your car keys the target and everything else a distractor. So if, for example, in this picture on the left-hand side, I said, can you find the dead tree? And can you find the satellite dish? The dead tree and the satellite dish are your targets. Everything else in this picture is a distractor. And there are 2 broad categories of visual search. One would be a feature search. You're identifying an object that differs along one dimension. So for example, color. I said find the red T in the background of the blue C, or the blue T's rather. Conjunction search would be looking for a target specified by a combination of features. Frequently in visual search tasks, it's 2 features, but you can have as many as you wanted in there. So you can see on the left-hand column, you have this feature search. All right, so if I said find the vertical red bar, maybe I said find it against a backdrop of blue vertical bars, Or maybe I said find it against a backdrop of horizontal red bars. Or I added more blue bars in there. This is what we call, in addition to calling it a feature search, we call it a pop-out search. The reason we call it a pop-out search is because the answer essentially just pops out to you. You're not really having to search anything. It's automatic. I said find, as long as you don't have any color vision loss. If I just said find the red bar on this left column, you didn't have to spend any time looking. You could just orient right towards it. And so what you see on the bottom graph down in here is that it doesn't matter how many objects you add to that search. The amount of time it's going to take you to search is going to be almost constant. It'll be constant for a set visual angle, but so when you look at the bottom versus the top, what you're seeing is that it doesn't matter how many blue vertical bars there are, that red bar just pops out just like that. With the conjunction search presented in the middle of those figures, if I told you to find the red vertical bar amongst a backdrop of blue vertical bars and red horizontal bars, it becomes a little bit more difficult because now you can't just do it off of color, or you can't just do it off of orientation. You have to do it off of color and orientation. So the blue bars are distracting because of the orientation. The red bars are distracting because of the color. And so it's going to take longer in this conjunction search, sometimes also called a serial search. Cereal spelled like killer, not breakfast. You can see that as I add more distractors to that visual search, it gets harder. You've got more things to search. And that's reflected in the actual reaction time it takes you to find the object. As set size increases in a conjunction search, so too does the reaction time to find things. However, you can also have a spatial configuration search. So one strategy for this conjunction search is essentially ignore anything that's blue, right? Just search for the red bars. Now you've cut down the number of distractors essentially in half with your approach. However, on the right-hand side, right column, you're told to find a T in any configuration, any orientation rather. And so what you're having to do is look against this backdrop of L's that have similar right angles. And you can see that the number of objects or the number of distractors added increases the amount of time it takes to find that object, that letter. And it's going to take longer for a couple reasons. One, it's a more complex figure than just a bar. But two, you're not able to essentially disregard half of the distractors as a function of the color of, for example. And when you look at the actual graphs themselves, you're going to see two lines. Right? The feature search line is just going to be overlapped with one another. But you can see a target present and a target absent line. And you can see that the target absent line is about twice the reaction time as the target present line.
That's to determine whether it's actually there, or
I'm sorry?
to realize that it's not there.
Yes, exactly. Yeah. And so why would that be? Why should it take twice the amount of time to realize something's not there as to find it on average?
Every other object is not being it.
Exactly. Yeah. If you just look at probability, you're going to average finding that target halfway through the trials, right? Because some trials you may find it the first one you search. Other trials you may find it in the last one you search, and everything in between. But that's going to average out to having to search about half of the distractors to find that target. But when that target's missing, you're searching through all of the distractors every time. So again, you're getting distortions of the amount of time it's going to take as a function of what type of search it is, and a distortion of the amount of time as a function of whether the target is there or the target is absent. So really quickly, search this and find the egg in this picture. All right, so if you haven't yet found it, that's where it is. So what type of search would this be?
Spatial.
Sorry?
Spatial.
Why spatial?
Takes longer to look for it because everything looks kind of similar to each other.
Okay.
All the rabbits are about the same shape as an egg, except they don't, like the egg only doesn't have ears. So you're looking for something smaller, the same shape as all of the rabbits that are in them.
I was thinking more along the lines of the egg looks like the ear to me.
Egg looks like a what?
The ears to me.
Yeah, so I can see why you would say spatial. The reason I'm going to say it's not spatial is because it's not necessarily the orientation of it that's going to potentially matter, or the orientation is not the only thing that matters in here. It's a conjunction search in that you're looking for the color, and now it's relying on a presupposition that an egg's going to be somewhat of a kind of off-white color, and it kind of is an off-white color, right? So if you're relying on that presupposition, it's a little bit more of a conjunction search. But I think you can make the argument that this is a spatial search. And again, that feature search, when I present that trivially easy task of finding the red bar against the backdrop of blue bars, takes place in parallel. Right? Your brain is essentially searching through everything at once because it knows it only has to find one thing. Right? So that's that pop out. You look at it, boom, it pops out. All that processing took place in parallel. The conjunction search and that spatial configuration search are again conducted in that serial manner. All right, so what you're having to do is look at every single object and establish, is this my target? So whereas in parallel, everything's processed at once, in a serial search, you're having to go through and look at each one of these. And because you're doing that, the more distractors you have, the longer it's going to take. Any questions about searches so far? Or anything we've talked about today? Cool. You're on Zoom and you do have a question, feel free to unmute yourself or type them into that chat box. So Anne Treisman, who unfortunately just passed away a couple of years ago, popularized what's known as the feature integration theory. Feature integration theory suggests that some features are processed in parallel quickly. And that's occurring prior to our attentional resources being devoted to them, right? So that pop-out search, you're not having to put in any effort, it just pops out, right? It's that flashing red light, just pops out. And others are requiring that deliberate, effortful attention, like in the conjunction search. So whether you like it or not, in that feature search, you're going to find the right answer, right? It's just going to come out like that. But Waldo is never going to pop out in a Where's Waldo book. Right? You may get lucky and just have your eyes look right at Waldo, but there's never going to be a pop out of Waldo. So again, these pop outs, we're using a lot of different names for the same phenomena. Pop out search, parallel search, feature search, all mean the same thing. You can see, again, these pop-out effects, these pop-out searches represented here. Side note, I think I talked about this maybe earlier in the semester, but Anne Treisman was part of the world's greatest, at least psychology power couple ever. She's one of the biggest names in visual search, visual attention, visual sciences, and her husband, Dan Kahneman, won the Nobel Prize for behavioral economics research. So they have kind of established themselves, in my mind, as the greatest couple of all time, at least in the modern era. But back to the science. So again, when we talked about that attentional spotlight last time, wherein you are fixating on something specifically and you're moving that around to accommodate.
Is orientation supposed to also go to attention spotlight?
Sorry, one more time.
Is orientation supposed to also go to attention spotlight?
What am I looking at here?
The orange box that says orientation does not
Oh.
have a line that goes to the attention spotlight. Is that intentional?
Let me think this through here. No. No, this is a poorly made graph as is because it has overlapping things. So I suspect, actually, I think you can see
The
just
orange line is right under the green one.
Yeah.
Sure
Yep.
it is.
I think if you look close, you can see it. I'm not just making that up. Look at your slides. But no, the orientation should go to the attentional spotlight. Where was I? Oh yeah, so the attentional spotlight is fixating on different parts in that field, that visual field. Picking up on what are those things of color, orientation, which has a line going to the spotlight, of motion, of curvature and depth. right? And Treisman's feature integration theory suggests that we're then combining all of that into a single object. Right? We're looking for the blue T. We're integrating all the feature components in addition to that color, and resulting in that object perception. Then interfaces with that object recognition is what we're in fact looking for. Yes? Great, we're done. All right, so critical thinking activity. What are some real-world tasks that you perform that are pop-out searches? And what about real-world searches that are conjunction searches?
I guess the exit button on your web browser
Okay.
would be a feature search.
Yeah, so if it's a red button, yeah, exactly. Yeah, so if you're looking for the red exit button, or the X, or whatever they present now, I think Apple did away with all of the iconography. I think it's just like a red circle. I could be wrong with that, but I think they have. Yeah, that is a feature search, right? They're trying to limit the number of things that are red on your actual display, so it just pops out like that. Who can give me an example of a conjunction search in the real world?
It would be like searching for your car.
Yeah, so searching for your car out in a parking lot. Right? I've got a silver Toyota Tacoma. Nobody egged my car if you see it out in the parking lot. But yeah, when searching for my car in the public parking lot, there are a lot of silver cars. There are a lot of trucks. There may even be some silver Toyota Tacomas. But I have to look for maybe the bumper stickers I've got on my truck. Exactly. Questions about what we've covered so far? Awesome. All right. So another paradigm that we can study attention with is called the Rapid Serial Visual Presentation, or RSVP, in which a series of stimuli appear quickly in time in the same point in visual space. So whereas the visual search we just talked about was a spatial search, the RSVP is a temporal search. And these paradigms will switch slides potentially as quickly as every 100 milliseconds. So 10 times a second. Again, if I present a series of images rapidly at the same place in space, and then I ask you to press a button or a key or whatever that trigger is, as soon as you register seeing that target, we'll get something like this paradigm here, wherein you're told to look for a white letter, and they're going to present a series of blank images and then also black letters. Right, as soon as you see that white L there, press that key. And so one of the really cool things about doing this type of task is we can learn some interesting things about our attentional system. And one of the cool things is what we call this attentional blink. Attentional blink suggests that I get the slides, target comes up, and then now they move on to other slides. I am likely to miss or be slower to respond to a second presentation of that target. All right, so if I say, press the key every time the target comes up, I press the key, and then a couple slides later, another target comes up, I'm likely to actually miss that second target because of this quote-unquote attentional blink. It's almost like your brain is just purely blinking. It's like, okay, we've got the target, take a second, reset, and start searching again. Right? And so in that 500 millisecond window, you're likely to miss that second key. How do they determine you're likely to miss it? So in this paradigm, I've got that white L here, and let's say there was a white H here, and I tell you to press the key every time you detect it. You're going to get one key press, but you're not going to get a second key press.
Right, but so I guess you're changing at a rate faster than 500 milliseconds.
Yes, yeah. So if I present, so if the temporal distance between these was 400 milliseconds, half a second roughly, you're likely to still miss that second one or not report seeing it. Good question. And this can be kind of analogous to that inhibition of return that we talked about last time with that Posner queuing paradigm, right? Your brain's essentially, it's saying, I found it, let's take a second. And then it goes right back to searching. But in that period, that latency period, that down period, you're likely to miss or take longer to respond to those stimuli. So, and so it's not necessarily just that we don't register seeing it. It's that we can have distortions in our actual processing in our brain. One of the really cool things is that I can tell if you actually see an object or see that target by single cell response or single cell recording in your V4, right? So if you see something in your visual field, by recording the specific cell that would be attuned to that object in V4, I can tell whether or not you saw it without registering a response. Getting a spike in the excitation of that cell. Right? And so when we talked about, I'm sorry, total brain fart here. So when we talked about the Simon's gorilla illusion, right, that attention placed in specific ways can affect your actual processing of your environment. And so if I hook you up to a brain scan and I'm looking at your occipital lobe on both the left half and the right half of your brain, I can tell to which side you are paying attention, even if you're not shifting your eyes. Actually, explicitly if you're not shifting your eyes. And so the right half of your occipital lobe processes information from which side, the left half or the right half of your visual field?
The right side processes from the left half. The
Yes.
left side processes from the right half.
Exactly, yes. So the right half of my visual field is processing the right half of my retinas, which are receiving information from my left half of my visual field. And so if I had you stare at a fixation cross, again, right in the middle of the screen, a fixation cross, and then I said, you know, shift your attention, or I presented some sort of cue to shift your attention, I can tell to which side you are now paying attention as a function of the activation in that corresponding hemisphere. And there's some really interesting examples of lesion patients, stroke patients, patients that have damage or missing part of their brain. And one such example would be those that have what we call hemifield neglect.
When you ask them to draw a clock, they draw it all on one side of the computer.
Yep, exactly. Yeah, and so you can have these lesions that results in a patient essentially completely neglecting, for example, the left half of their visual field. And so if I told a patient with hemifield neglect to look at this horizontal line and draw a vertical line down the center of that line, what you see is they've essentially drawn a line down the center of the right half of it. Right? They're neglecting the left half as if they don't see the left half of that line. Similarly, we can do what's called a cancellation, right? So I give them a series of lines and say, okay, every line you see, just draw a perpendicular line to it, or through it rather. And again, what you see is they're only canceling the objects in the right half of their visual field. They're neglecting all of those lines. It's not that they see them and can't follow directions, it's that they don't see them. Similarly, if you present a clock, you're getting essentially complete neglect of the left half of that clock or the left half of the house.
They don't try to scrunch the other numbers in
So
the clock.
what they're asked to do is not draw a clock necessarily, but they're asked to draw a clock that they're looking at, right?
Okay.
And so, so like conceptually, they can know that there are 12 numbers on a clock.
Right.
But so again, it's an issue with attention, not memory, right? So if you ask them to draw a clock, you ask them to draw a house, what they would be doing is from memory, and they could do it from memory, no problem. But if you ask them to look at this clock here and then draw that clock, that's how you get the image on the right half. Somebody apparently sold my phone number. I'm getting all sorts of spam text messages, some of which are nonsensical, but others are unpleasant and targeted. All right, so one of the other disorders with this sort of attention is what's known as Balance syndrome. And it's where you're getting function in both the left and right parietal lobes being compromised. And I'm going to show you a video of this in just a second, but it limits an individual's ability to localize objects in space. Difficulty coordinating that motor movement to grasp the object. And there's also frequently kind of a static eye position, right? So they're seldomly moving their eyes around in their environment. One of the examples you're going to see in just a second here is an example of simultegnosia, right? Or this fixation on an object that is directly in front and ignoring the object that is behind. So if I, for example, held up my water bottle to somebody with balance syndrome and then put my hand behind my water bottle, you all can see that my hand is behind my water bottle. However, somebody with balance syndrome wouldn't see my hand. They would just see the water bottle, right? It would be like an extreme example of Simon's gorilla study, where they're just, you didn't see the gorilla, right? So think of it in that same way. The gorilla was there, you just didn't see it. Let's see if, there we go, perfect. All right, so I'm going to show an example.
I can grab it with that hand.
Actually, let me stop the share real quick and make sure I am sharing. Perfect. World. All right, here we go.
I can grab it with that hand.
You can see when reaching for that object,
I can see,
right
but I
hand.
can't tell. I can't reach it.
You seem to do better with your left hand. And take a crack at it up here, if I hold it up closer. All right, how about now that you've touched it with that hand, can you reach with the other hand and grab it? With your right hand?
With my right hand?
Uh-huh.
So there seems to be
No, I can't.
a little bit more hemispherical
If I
issues
wiggle it, does moving it help you at all?
Nah.
on the left half of his brain.
Yeah, it does a little bit. So motion sort of pulls you toward it.
So it seems like motion helps kind of localize the object there for him.
What do you see here?
A comb?
Mm-hmm. What do you see now?
Comb?
What do you see now?
Spoon?
Do you see the comb?
No.
Do you see the comb?
Yeah.
Do you see the spoon?
Mm-hmm.
What do you see now?
I see the spoon.
What do you see now?
Comb?
Do you see a spoon at all?
No.
Okay. Can you see what? Just tell me what you see.
I see what looks like a blackboard with some writing on it.
Mm-hmm. And there is a blackboard with some writing right behind us. So when you lost track of what was there, you picked up whatever was
You can see that example there. He lost track of everything that was in front of him and was fixated on that blackboard. All right? And so again, this is very similar to what you all experienced in that gorilla study, wherein the information was there in front of you, there was no registering it. It may as well have not existed. Okay? And so for this gentleman, when that comb was put in front of that spoon, he couldn't see that it was a comb and then a spoon, in the same way that you could see that it was a comb and a spoon. go. All right, there we go. All right, any questions about hemisphere neglect or balance syndrome?
How does that connect to face blindness?
Yeah, I'll get to you in just a second, Allie. How does it connect to face blindness? So face blindness is another disorder we're going to talk about, that it is specific inabilities to recognize faces. So it's not necessarily an ability to perceive faces, like you know it's a face, it's just you don't have that kind of like
Can't match it
recognition.
against anything else.
What's that?
You just can't match it against your memory of anything
Exactly.
else.
It's like every face you see is the first time you see that face.
Okay.
Yeah. So Allie says, you may have said this, but do they know why this syndrome occurs? Yeah, and so, whoops. So it's usually getting lesions in both your left and right parietal lobe, right? And so a lot of the disorders we're going to talk about throughout this semester are kind of very specific distortions, right? And so having like Broca's or Wernicke's aphasia, I think we've talked about that at this point, maybe not, I don't remember. But are distortions in ability to generate and perceive speech, right? And those are in very specific regions of the brain. Balance syndrome would be a very specific lesion in the parietal lobe. And so these lesions can occur for a variety of reasons. One of the most common causes of lesions are just strokes. And so you get brain death, parts of the area where you've stroked. All right. So every semester when I teach this part, I always want to have one of my friends bring in their kids, but I felt like during a global pandemic, it's probably not the best time. So you all have lost out this semester. But we can also look at how infants and newborns start to direct their attention and direct their gaze, right? So we can rely on this overt attention, right, the shifting of where your eyes are looking, as a relatively good approximation for your attention. And one of the things we can do is this, what we call an oddball paradigm, wherein we'll present a kid a series of balls and then present one different object. What we find is that in older kids and adults, our attention tends to be oriented or directed at that oddball object, that one-off object. However, in the younger kids, we don't tend to see that orientation to that oddball itself. Right? And so there are developmental issues of the actual continued development of your eyes, your retinas, which affect your ability as a really young newborn to resolve your world. But there are just differences in attention. So the presence of TV noise in the background is a lot more disruptive to an adult than it is to an infant, right? Because that noise attracts our attention, whereas infants tend not to have that same sort of attention grabbing.
They don't have as much process.
Sorry?
They don't have as much process. Like they don't understand the language, so they're not processing meaning behind the noise.
Yeah, so I don't know this specific study, but if I had to guess, what I would imagine is they're just noises. Now, you can even say noises have certain, paired associations. So, I mean, you hear a siren, there are certain things that go along with that. And so I suspect there is partially a meaning grasp to it. But my suspicion is that even when you present some sort of noise that would otherwise be attention getting, right, just some sort of, kind of loud attention grabbing noise, it's going to result in adults orienting towards it a lot more quickly than would an infant. But I don't know the study specifically. And we've already talked about these bistable images. For example, when we talked about figure ground assignment. But here are the three most kind of famous and popular. So the Necker cube over here, we tend to see in one of two orientations. We either see this face right here as being bottom left, or so bottom left and coming towards us, or we see this face here as top right and coming towards us. Right? But we can't see both of them simultaneously. You can flip back and forth between them, and where you look on the image is actually going to affect which one you see. But you can see this is a bistable image, right? We can see it one of two ways, but we can't see it both ways simultaneously. Similar, this rabbit-duck illusion. So you can either see it as a rabbit, or you can see it as a duck, but you can't see it both ways simultaneously. And then you have Rubens' vase, which is that face-vase illusion, where you're either seeing two people that look like they're about to kiss, or you see a vase, but you can't see both simultaneously. And you can get this kind of really interesting phenomena, this perceptual bistability, wherein I can present a static visual image that results in alternating perceptions, right? So in the same way that you could see the duck, you could see the rabbit. But you also get this kind of conflicting bistable image of sorts with your binocular rivalry. So if, for example, I presented a picture of a house on one side and a picture of a person on the other side, what you're going to see is either a picture of a house or a picture of a person. And you can flip back and forth between the two of them, but you're not going to see an overlap of those two. All right, and so if I presented these images here, right, and I had you put on those 3D glasses, so one image goes to one eye, the other image goes to the other eye. So a house goes to one eye, a person goes to the other, and I presented them together, you're not going to see what's about to pop up here, of that overlay of those two images. You're going to see either a person or you're going to see a house. And your brain can switch back and forth, and you can consciously switch back and forth, but you can't see them simultaneously. Right? And I think the best way to represent this is sometimes when you're laying down on the couch watching TV, and you've got a pillow under your head, and the pillow obstructs one of your eyes, you still see the image on the TV. Right? But if you close that eye, you'll notice that, for example, your left eye is completely occluded by that pillow. Right? And you can actually make yourself switch back and forth between the two of them but you're not going to see kind of an overlap of the images. And one of the really cool things is if we know what part of your brain processes specific types of information, we can tell what your perception is, what your attention is fixated on. So if I show that example of that house and that face together, and I, for example, did recording in your, what we call the fusiform facial area, FFA. What I'm going to see is an increase in the activation in your FFA when you are perceiving that face, right? When your attention is fixated on the eye that is perceiving that face, thus your resultant percept is of a face. What's that? Someone's in the waiting room? Oh, there. We're so late in class, it didn't even register that that's what you were talking about. Yeah. Although one of the things to note is there's some ambiguity about whether this fusiform facial area is actually specifically for faces or things we're experts in. And I say that because one of the leading proponents against the idea that a fusiform facial area is specifically for faces is actually faculty just up the road at Vanderbilt, Isabelle Gauthier. And I won't bore you with her studies, but I want to point it out because I think it's an important distinction to make. All right, so critical thinking, maybe. There we go. Why do we see these bistable images? Why can't we see both of them simultaneously? Or why would it make sense for us to have evolved in this way?
It would be harder to detect movement or notice individual aspects of the overlay.
Yeah, so it could be tougher to see movement, right, if you had things overlaid, right? But with things like the face and vase illusion, how would that play into that sort of benefit?
Camouflage.
Okay, so camouflage, yeah, absolutely. And then again, you can also think about the fact that our brains are incredibly hungry computers, right? Our brains take up a oversized proportion of our energy consumption every day. And if you're constantly seeing both things, you're essentially doubling the amount of potential processing that's required for your brain. Right? And the amount of attention it would take to hold simultaneously two different things in your head is difficult. Right? And we're not good at multitasking. Right? We're good at devoting our attention to one thing. Right? In the immortal words of Ron Swanson, don't half-ass two things, whole-ass one thing. That's kind of what our attentional system is doing. Not good at two things unless you're an expert, and so it becomes automatic. So that's something we talk about in cognitive psych or human factors, stuff like that. And now I'm a human factors researcher, human factors psychologist, and so what I'm interested in doing is applying a lot of what we know about the human system to, for example, display design, right? Or cockpit design. How do we remake things to be more user-friendly, easier to use, safer to use, resultant in better percepts? And so I want to talk about just some of these design principles using the information we have about attention. And so one example the things we want to do is minimize that information access cost. So remember, going back to that Sieve model, if the effort it takes to access information is greater, the likelihood, the probability that you're going to attend to that information is diminished. So think about when you're driving. Now, you're driving along, you want to switch lanes to get into the right lane. What's that?
So if you're a decent human being, so you put on your blinker.
Yes, well, you want to put on your blinker, absolutely. Now, what the book tells you to do is check your mirror and then turn around and physically check your blind spot. Now, what people do 99 point whatever % of the time is just check the mirror, right? Because the amount of information, or excuse me, the amount of effort it's going to take to access that information is higher if I have to turn my torso, my trunk, to actually look in my blind spot. So again, if something's in my foveal range, right, in my foveal region, no eye movements required, I'm much more likely to attend to that information than if I have to move my eyes. But moving my eyes is going to result in much more likely to attend to information than moving my head, which is going to be more likely to attend to the information than moving my trunk, right? And so that's why it's easier, and you are more likely to do it more frequently, to check your driver's side mirror, but also your rear view mirror, than you are to check your passenger side mirror and your passenger side blind spot. Similarly, you want to have this, what we call proximity compatibility. So objects that are related to one another, you want to group together. Because then nearness, again, is associating or conveying association and meaning with one another. Allows me to direct my attention towards something specifically and then begin my search from there. But as I've said, we have limited attentional resources. Right? We think about attention as a pool, and anything pulling from that pool depletes the ability for anything else to pull from that pool. Pull from the pool. Say that 6 times fast. One of the things we can think about is what's known as the multiple resource theory, which suggests that while attention itself is a pool, we tend to have kind of modality-specific reserves, such that you're going to struggle to process 2 sources of visual information simultaneously. But if I take one of those sources of information and make it auditory, you're now more likely to be able to process the 2 of them. That being said, again, attention is a finite pool, such that you shouldn't listen to music with lyrics while you're reading. Your attention is going to be geared towards one or the other, and too frequently it gets picked up by the song. Similarly, in the actual generation of answers or actions, you don't want to make too many actions require a verbal response, right? If you can have some other kind of code or modality by which you can communicate. So again, when we think about the mental models of displays, we want things that have similar controls to be presented together. Right? I want to be able to dictate to where my attentional pool is going to then be able to search from there. Don't require me to search the entire display for what I want to be looking for. Because now we're getting into a conjunction search that's going to take me a lot longer. And if I know anything I want to do with text is here, and now I've got a smaller set of distractors to search for. Again, thinking back to that multiple resource theory, avoiding that resource competition. So can we offload things to speech that may otherwise require our hands to complete? Right? Can we allocate controls to the left and right hands, between hands and feet? And again, keep in mind that if you have something that is attention grabbing, the consequence of that means something else is losing that attention. So don't have something that's very salient that's going to grab your attention if it's not all that important. Any questions from today's lecture? Awesome. Well, if there are any questions, let me know, and I am happy to hang out and answer them. Otherwise, I will see you on Wednesday, totally virtual, for, once again, another exam review session. So come prepared with questions, and I will see you all then.